All right, we're back. Question 18. Let's jump in here, grab a little bit of white space and see what we can do. All right. So again, I'm not going to go through all of these. Part of this, I mean, the class is to try to push you to get these. So if you have lines of symmetry um, through different pieces, I don't know which one I want to do. I'll do at least one of them here to kind of get you a nudge in the right direction. But if it had symmetries through a pair of opposite vertices, then you might be better off kind of drawing, here's my vertices, wherever they are, right? And I have lines of symmetry through them. So when I cut this one down, this one has to mirror over to the other one. This one has to mirror to that one. And when I cut this one across between these two, this one on top has to mirror to the other one on that side. So it does kind of tell us um, it does kind of tell us approximately the location of those pieces, and that might be enough to help you determine what kind of shape it is. So let's see here, two lines of symmetry through each pair of midpoints of the opposite sides. Okay, so I've got some kind of opposite sides, right? Something like this, because this would be quadrilateral. And here's the midpoints of opposite sides. So when I say I have a line of symmetry here, it means when I draw this line that this top point has to fold down onto this point, and the top one up here has to fold down onto the bottom point in the corner. It has to fold down. Okay. So that does tell you something, right? Okay. So that tells you the location of these other pieces, right? Because I have a total symmetry. So that means I couldn't have a shape that looks like this, right? I couldn't have that because this shape has to go down over onto this point. So that wouldn't be happening. All right, so let's take a look at what else we have. And that's true for the other one as well. So if I put a line here, this one comes down. Oops, that was a horrible line, but there's this one. Again, this point on the side has to flip over and map to this one. This one over here has to map to that one. There it is. So now I'm trying to find the most general name. Well, I mean, yes, a square would do that because if I did this, you're like, okay, perfect symmetry around a square. That's fantastic. Can I go bigger than a square? Right? Okay, so could I do a rectangle? Right? So now you're kind of pushing yourself a little bit. Let's look at a rectangle. Does a rectangle have this? There's the midpoint. There's the midpoints. Yes, it does. So I'm working my way up through that list of terms and the connections that we saw in class related to those terms. Let me jump back just a bit in the book and I can show you. Those are all the symmetries. Here we go. So we just showed that a square, yeah, square has this property. And we just showed that a rectangle has this property. We could ask, does a rhombus have this property, right? Well, I mean, you can take a look and see, right? If you want to do a rhombus, then here's a rhombus. And what you need is opposite sides. So if I take the midpoint of opposite sides, right, and I draw this line, do I have a line of symmetry? And no, no, you don't. You have a turn symmetry if you rotated it, 180 degrees, but this point would need to come out and be the same distance on the other side. So this point would have to map here. But instead, this point right here, this top ends up mapping down here, which that does not work. So a rhombus is out. If a rhombus is out, a kite is out. Okay. But now work your way up. Square worked, rectangle worked. Does a parallelogram work? Well, I need a general parallelogram. So then I could draw a shape that looks very similar to this rhombus. That would be more of a general parallelogram. Do I have it through the midpoints of opposite sides? And no, you do not. So parallelogram's out. Isosceles trapezoid. Isosceles trapezoid would be out, and you could do it for the same type of reason. It would look something along the lines of this. And through this midpoint, you're like, sweet, it does fold over. So this one's good. But the one going across to the other set of midpoints like this is not. This one should come up here, and it does not. This one should come up here, and it does not. So yeah, trapezoid's out, isosceles trapezoid's out, general quadrilateral is out. So the most general name would be like the highest ranking, and the highest ranking here would be a rectangle. And that's kind of the approach that I would take if I was doing these problems, is to kind of say, let me connect these ideas and see how they work together. Okay, let's see here. So that was 18. I think I have a few math connections here too. MC 2D. Okay, let's take a look. 2D. Wow, it's the always, sometimes, never. So just if you look at these questions, it doesn't look like an always, sometimes, never because it says something like always. In your mind, just come by and get rid of that. And just change it to an equilateral polygon is convex. Okay. Equilateral polygon is convex. What do you think? Does it have to be true? So if you're busy thinking, hey, yes, I think it does have to be true, I would consider pushing yourself to draw one. Think about some regular polygons that you know about. Maybe even I don't know. What else? What do all the kids do? Kids are driving these days, so you could think of a stop sign, right? There's a stop sign, and it's equilateral and equiangular. A stop sign is regular, but what if you took part of the stop sign and pushed it in, keeping everything else exactly the same? So all of this stuff stays the same, and then take the two lines that are right here and push them inward. And what you'll get is something that looks like this. Okay. And all of a sudden I have a shape that is concave. So that violates. Sorry, not going to happen. You won't see this until after you get past degree 4. You will not see this, well, I guess number of sides being 4. You will not see this on a quadrilateral. You see it on a pentagon and higher, but you won't see it anywhere else. So again, if you're getting stuck because you're thinking of triangles and quadrilaterals, push yourself a little bit. Say, hey, let me go a little bit bigger and see what happens. And then we have MC10. So here we go. MC10. Okay, I think it's 10. Let me double check. MC10. A student asks if ABCD is a valid name for the rectangle, then is ACBD also valid? Okay, so first off, anytime you deal with these student questions, you want to do your best to kind of say, what are they doing, right? Why would anyone think that this is true? Where is a possible misconception? So go to a triangle, go smaller, take a step and see. When students are confronted with new ideas in geometry or in math in general, they try to fit it into something they already know. And so when you're labeling a triangle, right? And you say, here we go. How would we name this triangle? Well, you could call this triangle ABC. Perfectly fine. And if you think about it, it's because I can connect in order A to B to C and then back to A. So we get this kind of circular path, and it demonstrates that I can connect all the way through. That's the smooth, excuse me, the smooth, simple closed curve. So there we go. ABC is there. Next up, we could do BAC, right? And once again, could I get from B to A to C to create this shape? Start at B, come down here. Yes, that looks good. Over to C, that looks good. And up to B. There we go. There's another way to name it. Okay. What else could we have? So I have ABC and BAC. Now that's the only way that I can have C show up at the end. That's it. So could I call this triangle CBA? Again, start at C, work your way to B, work your way to A, then back to C. That works. Could I call this triangle CAB? And you'd say, oh, C to A to B and back. Okay, that works. So what you're realizing is with a triangle that you really could write the letters in any way you want because it's always possible. Now think about what the student is actually saying here. You would connect the points from A to C to B to D and then back to A. So the shape they end up with looks like this. And you'd have to ask yourself if that is a valid name for a rectangle. Is this a rectangle? Notice a rectangle is a type of quadrilateral. A quadrilateral is a type of polygon. Is this a polygon? And go through the kind of that definition. It needs to be simple closed curve connected only by line segments. So this kind of helps, I think, visualize what the student issue is, but then work with the student, right? Say, hey, I like where your thinking is at. You're thinking kind of like a triangle. Maybe we could put it in any order. Go through and connect it, demonstrate that this is not valid, but then say, okay, I used, maybe you as the teacher used A, B, C, D, okay? And ask the student, can you come up with another name that's not exactly the one that I have, but would still actually represent this shape? Because there are a lot of different names, okay? A, B, C, D, B, C, D, A, C, D, A, B, right? D, A, B, C. All of those are perfectly fine. And all of those are going in kind of a clockwise motion. You could also go the other direction and make a counterclockwise claim, which would be A, D, C, B, and then continue making a list of all options there. So it turns out there are a lot of different names for these shapes, but you can't jumble all the letters with the exception of a triangle. And the only reason for that is if with just 3 letters, it doesn't matter where you start and where you go, there's only 1 point left to get to. So I think that hopefully will help the student to see, hey, I had a reasonably good idea, which they did. They had an idea to connect the idea of naming rectangles back to what they did for naming triangles. All right, that does it for here. Hope that gets you on the right track. Off you go.